Hello, stats friends. So our 1.2 lesson it's another big lesson. I think it's going to be split up into 2 days, so I'll try to give you a heads up as to where that split is. And this is adapted from Starnes and Tabor, The Practice of Statistics 6E, the updated edition. All right, so I skipped over the title. In 1.2, we're going to be displaying quantitative data with graphs. So we're going to show you different styles of graphs. And notice that the description here is this is quantitative data as opposed to categorical data, which is what we saw before. So just to remind you, quantitative data meant it was dealing with numbers. So here's our targets. All right, and this first idea, one of the displays that we will use often because it's just so nice, is a dot plot. So a dot plot should look really familiar because you use these a lot when you were little young ones. So it shows each data value above its location on a number line. And it's pretty simple. Draw a horizontal axis, also known as a number line, and label it with quantitative variable. It doesn't necessarily have to start at 0. It might, depends on what your data collection looks like. And then we scale it. In this particular data set is number of goals scored from, oh, I cannot remember which soccer team it was, but one of the big soccer teams. You scale the axis from the minimum to the maximum value, your range of your data set. And then every time one of those values occurs, kind of like a tally, but this time you would put a dot above it and you'd stack them up. So you can see shape in a dot plot pretty nicely. So now we're going to talk about how do we describe that shape. So it is roughly symmetric if the right side, the right side of the graph containing half the observations, is approximately a mirror image of the left side. So we're looking for symmetry where there's a peak in the middle. Now, this always confuses kids because it's kind of opposite of what some of you think. A distribution like this is called skewed right. And you'll notice that the length from the middle, which we're going to talk about as the median in a moment, or maybe tomorrow, I forget, coming up soon, though the median to the right is a longer section than the median to the left. So that's why it's skewed right. Now, when my husband took a stats class in college, he, like me, we have a difficult time remembering and we always second guess ourselves. So he said he thought of it as screwed up on the right side, is how he remembered it. And that's how I remember it now to this day. So I thought that was helpful. So skewed left would be the opposite of that. Your middle to the left end of your tail is longer than the right side, and that's why it's skewed left by definition. But by my definition, or Mr. Abruzzo's definition, it is screwed up on the left. All right, the direction of skewedness is towards the longest tail, not where the most observations are clustered. And that's what always confused me when I was a young student, because, like I said, I second guess myself a lot. All right, another thing that we will do to describe shape is the peaks. So unimodal, just to kind of break that down, uni meaning one, modal referring to the mode. So the mode would be the number that has the most tallies, essentially the most dots. And if it has one peak, then it's a unimodal is the description. But if you literally said has a single peak at 20, that would suffice. Bimodal means there's two peaks and you're going to see two clusters with them. It doesn't mean anything's wrong with your data, it's just you describing the shape of your data. And it might make perfect sense if you look at the data in the context. Now, a distribution can be considered symmetric, approximately symmetric, if all the frequencies are about the same. Now, notice this example here, they're not exactly the same, but if you kind of squint, they look kind of the same. So, sometimes describing the shape, we try to give you real obvious ones because we don't want anyone second guessing themselves. So here we have a check your understanding problem. I never pronounce names like this right. I had a student a child that I went to school with, and Knoe they pronounced it Knibble. I don't know if that's right. It's an amusement park in Ellisburg, Pennsylvania, has earned acclaim for being an affordable, family-friendly entertainment venue. Knebbles does not charge for general admission for parking, but it does charge customers for each ride they take. How much do the rides cost at Knebble? The table shows the cost for each ride in a sample of 22 rides in a recent year. Okay. Cool. All right. So what we're tasked with here is we're going to make a dot plot of this data, and then we're going to describe the shape of the distribution. So pause the video and try to jot down your own version of the dot plot and describe the shape that you see. In the next slide, you'll see the answer. All right, so stolen straight out of the book. This is the dot plot, and you'll notice when they scaled the axes, they started at 1 and went up to 3, even though there wasn't any ride that was 1. It's okay. Your scales can go a little beyond. We just don't want to go like too far beyond or miss anybody. The other thing I might point out is that they scaled by every 50 cents. That was their choice, and it's possible that, if you did yours, you put a marker at the 25ers. That would make sense to me. And then they tallied them up. So between 1 and 150 must be their 125. And then they put their dots on where they were supposed to occur. They stacked them. It also is important, and I only say this because I've done this, you want to make your dots or whatever marks you're using the same size. Don't get sloppy. Like sometimes I'll put X's and then I'll notice like my X on the first one is significantly different in size than the last one for some reason. And it's hard to see distribution when you mess it up like that. So just be careful. All right, so they are claiming that this distribution is skewed to the right. I agree with that. It does seem to be like stretched out on the right tail. And they're saying it's unimodal because there is one definite peak. There is a bit of a cluster around it, but the peak itself is at $1.50. And notice how they mentioned that. They said it's unimodal with a single peak at $1.50. There are two small gaps. I wonder if you noticed that as well. There was no data at 225 or at 275, and that's something that they pointed out in the shape. So when I answer questions about shape on graphs, if it's for like an AP question, I just kind of list out everything I see and hope for the best. You don't always want to just babble on your answers because sometimes you'll lose points for that actually. But when you're describing shape, as long as you're correct in what you're describing and you're not conflicting things, I think more is better in that case. So, what else are we talking about here? So we talked about shape. Now we're going to talk about the other important pieces, which are center, variability, and is there an outlier? So there are 4 things that we need to look at when we're describing our distribution for a quantitative variable. And those are those 4 things. Center, today we're going to refer to it generally as the median. Later on we'll talk about other things. Variability, today is going to be kind of lame. It's basically going to be a range, which is fine. We'll talk about more exciting things later. And then outliers would be something that is obviously falling outside of the overall pattern. So always include context as their tip for this, and that's really, really important when you're describing the shape. You notice on that previous example, they talked about, the single peak, unimodal single peak at $1.50 per ride. Like the mention of the $1.50 per ride was important. So do not forget that. So the the mnemonic device they use in your textbook to help you remember the 4 things we need are statistical opinions can vary. Oh man, someone told me another one. I'll have to look that one up. But there was another one that someone taught me this summer, and I thought that was cute too. But shape, outlier, center, variability. Not necessarily in that order, but just got to make sure that you answer all of them. So here we have an example. Describe the distribution of goals scored in 20 games played by the 2016 U.S. soccer team. There we go. Women's soccer team 2016. So this is their dot plot. If you could describe the distribution, think to yourself, even pause the video if you want to take a moment. I think yeah, there we go. All right, so the shape is skewed to the right. Okay, so you see that skew. And there is a single peak at 1 goal. And there is a gap, a pretty decent gap here between 5 and 9 goals. Now, that was just shape. We haven't talked about the outliers yet. That's a different bullet point here. Like that one. So the outliers, there seems to be 2 outliers, right? When the games when the team scored 9 and 10 goals, those appear to be outliers. Now notice the words appear to be outliers. Nothing definitive there. We don't want to say they are outliers because we're going to learn later that there's actually a test for that. The center, they're going to describe as the median. So just to remind yourself, the median is the middle. Now there's an actual formula for how to find the median, and there's a active way you can do it where you cross off first, last, first, last, first, last. But the idea is the middle of 20 games. And this always confuses kids. They're like, is it 10? Is it 9? Is it 11? Which one is it? Think of something smaller. So if you had 3 games, the middle would be your second game, right? If you had 5 games, your middle would be your third game. So what I do is I think about how that mathematical pattern works, and the idea is you go um, like, one more up, and then you cut it in half. So 21 cut in half is, yeah, that's a math teacher problem, huh? 10.5. So you're like, how do I get 10.5? Well, it's the average between the 10th and the 11th. So if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and it was a moot point because 10 and 11 are right here. So the median is boom, right here, 2 goals scored. The variability, in this case, all we're capable of answering to is just how spread out the data is. So the number of goals varies from 1 to 10 goals scored in a single game. And those are the 4 attributes that we must discuss. Did we include context? You bet we did. Look at all that. Goals, 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 team, goals. Perfect. The biggest mistake that I find myself making is I'm kind of a fast, sloppy note taker and writer, and I don't take the time to put good context in, and I need to do better. So comparing distributions, we're still on day one's lesson. Let's look at these 2 dot plots. They're kind of stacked on each other. What do we got here? Census at schools, random data selector. That must be a thing. I don't know. They keep referencing it. To choose 50 students from each country. Here are dot plots of the household sizes reported by the survey respondents. Compare the distributions of the household size for these 2 countries. So this time, instead of describing a single distribution, we're comparing the 2. And again, context, context, context. Here we go. Oh, well, before that, AP exam tip. When comparing distributions of quantitative data, it's not just enough to list the center variability. You must explicitly compare these values using words, greater, less than, lesser, more than. That wasn't an word, but you get the idea. About the same as. So you must have comparative language within your description. All right, let's see what they did here. So for shape, the distribution, now notice the context here, the distribution for the household size for the UK sample is roughly symmetric. Oh, I got nervous for a minute because I thought this was UK. This is UK. All right, roughly symmetric, agreed, with a single peak that must be at 4 people. The distribution for the household size in South Africa is skewed to the right, with a single peak also at 4 people. There's a clear gap, and they didn't specify, but still in South Africa, a clear gap between 15 and 26. So that was describing shape comparatively with context. Now, as far as outliers, there don't appear to be any outliers in the UK distribution, but in the South African distribution, there appears to be, and then this might confuse you if you called the 15 an outlier. At the very least, I think we can all agree that 26 is an outlier. 15 is probably an outlier, but again, that's why we use that language that says there appears to be. So there appears to be some outliers at 15 and 26 people for the South African distribution. All right, now let's talk about center. So I forgot what it was. Was it 50? So it was 25 in each? I can't remember what we did. Oh, 50. Hello. So for center, midway to 50 would be around 25-ish. Oh my goodness gracious, I should be able to count, huh? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So right here would be the median at 6 for the South African distribution. And then I'm guessing the median's in here, but if I counted to 25-ish, it would be here on this giant one here at 4. So the median for the UK distribution was 4 people. So notice they didn't just say, here's the median, here's the median. They said household sizes for the South African students tend to be larger, or there's your ER word, because they have 6 people than the UK students with a median of 4 people. That is the key part to that comparison, the ER word there. Okay, variability. So household sizes from South Africa vary more. It's not an ER word, but it is a comparative word. So they vary more because they stretch from 3 to 26 versus the UK data, where their household numbers stretch from 2 to 6. So far less variability in the UK data. Okay, so did we have context and comparative language? You bet we did. I didn't go through and highlight all of them, but we should, huh? We'll do that in class, I bet. All right, let's check our understanding. So we have 2 dot plots comparing to again, we've talked about this before. They take a very binary approach to gender for these problems because it just simplifies their statistics. When you open up your statistics to consider other types of genders and other gender identity uh, I can't think of the word all of a sudden, gender identities, then it doesn't make a worse or better problem. It's just a different problem that we can analyze the data further. So if in the context of the problem, we want to talk about students that identify as something other than male or female, we just separate that data. Easy as that. So for a stats project, Jonathan and Crystal hosted an ice cream eating contest. Oh, these are my people. All right, each student in the contest was given a small cup of ice cream and instructed to eat it as fast as possible. Jonathan and Crystal then recorded each contestant's gender and time in seconds, as shown on the dot plot. Compare the distributions of eating times for males and females. So remember, we're still using those 4 attributes, but we're going to do it in a contextual and comparative way. So stop the video, write down what you think you can come up with for shape, outliers, center, variability, not necessarily in that order. Make sure there's context and make sure that you have used some comparative language and some ER words. All right, so shape. The distribution time for the female sample is skewed to the right with no clear peak. So skewed to the right. And it's hard to say that there's a peak because it's not unimodal here, right? Ding, ding, ding. 3 of them right there that are the same height. As compared to the male sample, which is skewed to the right and does have a single peak at about 17.5 seconds. So here's their single peak. We still have that skewed to the right. There's always that one person who eats their ice cream slow. I didn't highlight all the good context, my bad, but it's there. I hope you see it. All right, the outliers. In the female distribution, there appears to be one outlier, the female who took 105 seconds to eat the ice cream. What are you doing, girl? All right, the male distribution does not appear to have any outliers. Again, someone might say, oh, I think these are outliers. Because they're kind of clustered, that's typically not considered an outlier. But if you wanted to claim it, I don't know that they could argue with you at this point. Again, we'll have a test for outliers later. But this lady over here, she would be an outlier for sure. So the center, the time it took females to eat ice cream was generally longer, and they're claiming the median was 45 versus the male median, which was 20 seconds. So, oops, back up. Did they tell us how many people? Oh, for Pete's sake. All right, some people are really good at this and they can just like eyeball it. They're like, here's the median. I am not that person. If I had to guess, I would say the median is like about here and about here. But I actually go through and I count them. Isn't that terrible? So either way, they did give us context and comparative language here. They said the time for female students to eat the ice cream was generally longer because the median was 45 seconds versus a male student's median from their data, which was 20 seconds. What did you do, dudes? That was really, you're going to get brain freeze. Calm down. All right, variability. The times for female students vary more from 13 to 107 seconds versus the male students who took about anywhere from 5 to 50 seconds. So again, they're just commenting in a comparative way with context on the range of data for male and female distribution. There we go. That's it. You just got to write a small essay and then you're good, right? Yeah, I know. It feels like a lot of writing. Hey, at least there's a formula to it, right? You know what you have to have. All right, so I think we're still on day one. Hang with me. We're going to talk about stem plots. Stem plots show data values separated into two parts. They're very adorable. They're called stem and leaves. So a stem consists of all but the final digit, and a leaf is the final digit. So the stems are ordered from lowest to highest, arranged in a vertical column. Excuse me, I'm yawning. Ooh. The leaves are arranged in increasing order out from the stem. So I'll show you an example in a moment. Separate each observation, consisting of all but the final digit and a leaf and a final digit. Okay. Write the stems in a vertical column. We just talked about that. All right, let's see this. Let me show you what's going on here. So we have this data. These are 20 female AP statistics students who answered the question, how many pairs of shoes do you have? This is I feel like it's a sexist question, guys. I've met a lot of men and boys who have a lot more shoes than girls do. So come on. What you trying to prove here, man? Anywho, I would like to see the side-by-side stem and leaf comparison. So what they did is they noticed they had two-digit values, nothing but two-digit values. So the stems will be the tens digits, the 5, the 2, the 2, the 3, okay? And the leaves will be the numbers that occur after it. So stems, they range anywhere from the teens up to the 50s. It'd be nice if these were in order, but they're not. So then you start creating the leaves. So I usually start I guess it doesn't technically matter, but they're supposed to be in order, so that's kind of obnoxious. So I go find all the teens, right? We got a 13, a 13, a 13, a 19. So what we're going to have to do now in leaves is list those out. And then they didn't. Oh, I missed a whole bunch. Oh gosh, there's another 13 and a 15. Oh gosh, fire me. All right, so what you'll notice here is they added the leaves, and that's great, but they are not in order. So then they'd have to reorder them. You know, that's a lot smarter than how I do it. I like painstakingly try to order it, and I always screw it up. So I should do what they do. That's much more of a time saver for me. Um, Clearly, it, you're not supposed to draw in your textbook, right? Especially you guys with class sets. But I usually make a mark on the chart. Oh, that's awful. I shouldn't do that though. But use pencil and then go back and erase it so the next kid doesn't see it, okay? Because that's obnoxious. So what we also have to do in a stem and leaf plot is give a key somewhere on the problem. And you'll literally write key and then you'll give an example. You say 4/9 represents a female student who reported having 49 shoes. So that way someone who just walks in and looks at your stem and leaf plot, they know how to interpret it. Oh, see, I knew they wouldn't be sexist. Starnes and Tabor, you're too good of authors for that. All right, so what we're going to do here is we're going to compare the female and male data using well, two issues are going to come up here. If you've got bunched up data, you can get a better picture of the distribution by splitting the stems. So if I look back at this data here, I notice like the teens and the 20s, they're really kind of clustered together. So what they're going to do is they're going to split your stems. So there's two of each stem. And the first one will be for the ending digits of 0 to 4, and the second one will be the ending digits of 5 to 9. And then the other issue is because we're going to try to do some comparison, we're going to do a back-to-back stem plot. Fun! All right, so this is what it looks like when they split the stems. They literally just write 2 of everything. So notice in the male's data, there was some singleton digits, so they got to add the 0, 0. Now, because we're doing back-to-back, you're actually going to put a line on each side of the stem. Isn't that cute? And then notice in the top stem digit, it's anything 4 and under. And the second one has 5 to 9. Okay. So that's how they're splitting the stems. And you'll notice they put labels at the top so you know what you're looking at. So males are over here on the right side for the leaves, and the females are on the left side leaves. Again, they have a key. So now what this back-to-back stem plot allows us to do is do more of a comparison. And now that we've also split the stems, that helps quite a bit, I guess, kind of, maybe. It probably helps with the guys' data more than the girls' data. The guys have a big cluster here that kind of got clumped together, and now we can kind of see it more. The girls' data still feels a little clustered, but that's okay. We're not going to split it more than that. So as far as comparison, you can talk about the same sort of things that you described for the other displays, right? It's a little more annoying to I don't know. I guess it's not any worse than a dot plot. I really don't like finding the median. Oh, I'm sorry. I don't like finding it by hand. I'll put it that way. All right, so here's a stem plot of the percent of residents age 65 and older in the 50 states and the District of Columbia. So that'd be 51 entries, huh? And there's a key there. It's super blurry. It says 8/8 represents a state in which 8.8% of the residents are 65 or older. That's really, the key is really key, guys. Yeah, duh. It's really important because for someone just walking in, if they didn't see that key, they might think 6/8 meant 68%, but it's really 6.8%. So that's important. All right, so there's the stem plot. We're supposed to answer a few questions. The first one being, the low outlier is Alaska. What percent of Alaskan residents are 65 or older? So the low outlier, remember this is the low, that represents 6.8%. All right, don't look. I'm about to show the answer key, okay? Yeah, 6.8%. All right, back up. All right, number 3, ignoring the outlier, the shape of the distribution is. So this is something we'll be able to do where we literally ignore the outlier. So if you just look at this, it looks pretty symmetrical to me, and it seems to have this peak at the 12 percentages-ish, the 12s. I don't know how to call that. All right, so I'm thinking roughly symmetric. That's all they wanted. I should have read the question. Yeah. All right, and then the center of the distribution is close to, see, this is where they get me. Now, these are pretty close to each other, and that, to a person who doesn't like finding the median, that's pretty mean. Um, so, yeah, what do we say, 51? So that would be 26th. Oh, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. 12.8, is that an option? Yeah, C. All right. So in that case, we really did have to take the time to count it. Yeah, I mean, I probably would have eliminated down to that one. But like I said, guys, by the time I count it, I'm done and I don't care anymore. With my luck, I'll get some stem and leaf plot that's gigantic. All right, this would be the beginning of our second day's lesson. So if you're looking for the first day only, you can stop there. Histograms. So histograms, not the same thing as a bar graph. They're going to show intervals of values as a bar. So you're going to notice the axes at the bottom. And right here, they have a dot plot. They're going to show you in a minute how they change that. But the intervals at the bottom are going to be range of values. You guys have definitely seen histograms in your past, right? This is a histogram. So they're evenly spaced out. I don't want to call them bars, but they're bars. And you count the frequencies or sometimes the relative frequency within each of those categories. Classes, they call them in a histogram. So, how to make a histogram? Well, this is very obnoxious to me because I really hate doing these by hand. We're going to show you on the calculator how to do them later. But you want to define your classes and notice the inequality symbols. So 0 to less than 5, meaning up to 5, but not 5, because 5 is going to be included in the next class. You can't have overlap because if you actually had a 5, you don't want them to fall into two different classes, two different bars. That wouldn't be appropriate. I run into this all the time when I go to do logic in my Google Sheets and Excel, where I'm like, okay, conditional formatting, do this if your answer is up to this, and then I forget about rounding and it's a hot mess. So this is a challenge of my own. All right, choose equal with, make a table that shows the count or the frequency, and sometimes we want relative frequency. Draw the horizontal and vertical axes and label the axes. Okay, so this time they're going to do just a frequency histogram, because it says number of states up the top. And then they appropriately labeled and scaled them. That's, we talked about them being misleading sometimes. So they went with intervals of, and again, it's a little confusing because it shows like starts off of the beginning. Did you notice that? There's nothing right here. It starts right here. So 0 to 5, but remember this bar that we're about to graph is up to 5. So they don't count. It's not inclusive on the right endpoint. That's typically how they do the classes. And then you draw your bars, right? We can do that. And we can easily see the distribution when it's drawn that way. So don't confuse histograms with bar graphs. Remember, bar graphs were for categorical data and histograms are for quantitative data. Use percents or proportions instead of counts when you're going to compare distributions with different numbers of observations. We talked about that last time. It's the great equalizer to do a relative frequency rather than a frequency. If one of your samples has 28 kids and the other sample has 52 kids, it's not fair to just look at the counts. Just because a graph looks nice doesn't mean it's actually a meaningful display of data. So sometimes the graph is misleading even though it looks pretty. So we're going to be doing a lot on our calculator, and you are very much welcome. I will ask you to do it by hand, sorry. But you are also welcome to, I do this all the time. I check them on my calculator. So we're going to go through this a lot in class, but the idea is here's a bunch of screenshots and it tells you what to press. Again, some of you have different calculators, so the keystrokes might be slightly different. You're going to enter your data into the stat menu by choosing edit and then enter into list 1. If your list already has data in it, the easiest way to clear it out is just to go up to the name where it says list 1 and then hit the clear key, not delete, but clear, and then scroll back down. It'll empty the list out for you. So we'd be doing this one in class where we're going to take this data and we're going to enter this into list 1. And there's more data. Oh, great. All right, so we're going to take the time in class to actually do this. We're going to enter it into list 1, and then we're going to turn on our plot and plot a histogram with our calculator. So we need to go to second y equals, which is the stat plot menu, and that's where you can do a lot of the toggling and turning on of every feature you want. So I turn the plot on for plot 1, everything else is off. The choice that I want is the one that looks like a histogram, and I need to tell them where I put my data. Well, I should have at this point put my data in list 1. For the newer calculators, it gives an option for a frequency list. We didn't do a frequency list, but we'll see possibly in the future where frequency lists are very helpful. Today's not one of those days. So you can actually leave this as a 1. It's not a list, excuse me. A 1 just means everything I entered shows up once. If we have to use a frequency list, I will definitely show you guys that. And of course, you can be an individual and change your color. All right, so this part, you want to make sure your window looks pretty. And we didn't do this at the beginning, but we should have gone to y equals and made sure nothing was being graphed besides the histogram. But hit zoom and then choose zoom stat. I think it's 9. And it'll automatically adjust your window so it looks pretty for the distribution. And if you hit the trace key and you keep hitting trace, it'll bounce from class to class to class to class to class. And it'll tell you exactly where your classes are set up. Now your calculator makes that choice for you as far as like how to set up the bars, and it doesn't always make a lot of sense. So, I mean, it might make sense. I don't know. I don't know that the AP judges will ding you for having a weird class like this because you're not wrong. I think what they're going to notice is, oh man, this kid definitely used their calculator. Like they're going to know that. So if you're trying to make something that looks more by hand, maybe adjust your classes a little bit. So if you press a window and enter values shown for X, min, max, there we go. So this is them adjusting their window. Where are we at here? Graph. Yep, and then do the same thing. It'll adjust the graph once you adjust your window. So I'm not sure where that one started. A very strange 1.8, I guess. All right, so they adjusted that. Good on them. All right, exam tip. If you're asked to make a graph on a free response question, be sure to label and scale your axes. Unless your calculator shows labels and scaling, don't just transfer what's on your screen to your paper. So that's what they did in this example. They went with the calculator one at first, and then they adjusted it a little bit, so it made a little more sense. You can manually adjust it. That's usually what I do. Because who would start their class at 1.8? That's weird. All right, so let's check our understanding. In class, we're going to be doing this one together. Pause the video and check this out on your own for a moment. Maybe do it by hand, maybe check it on the calculator. And we're going to construct a histogram that displays all these IQ scores, and we're going to describe what we see and is the distribution bell-shaped, because the reference here is that IQ scores are supposed to follow a bell curve, which we'll learn later is a normal distribution look. But is this really how it's distributed? So they took 60 fifth graders chosen at random from one school. That's not a very good sample, but that's okay. All right, pause the video and try. So this, again, stolen right from the book. And they made the classes go from 80 up to 90, 90 up to 100, 100 up to 110, and so on and so on. So they're equally spaced out. And they did a tally count. They didn't show the frequency table, but they did show the end result here of a histogram. So here's one possible, notice possible histogram. If your classes are different, which I think 80 was like 81, 82. I'm not sure why you would start your class at something other than 80, but I guess you could have. If your classes weren't, 9-ish, 10-ish units apart, as far as size, if you had a different width, then maybe your distribution looks a little different. But this is what they went with for the author's answer. So the distribution description here, it does look pretty symmetrical and bell-shaped. Has a single peak, and that would be in the 110 up to 120 range. And there's no obvious outliers. The typical IQ score appears to be between 110 and 120. And they reference the median. Now, again, you could do the little count. Counts are a little easier for me on histograms because I know, like, if I need to be at, I'm obviously making this up, but what do we have? 60. So if I need to be at like the 31st number, this is 3 and this is 4. So already I'm at 7, Here's 14, that's 21. And then the 30th one would be in this bar here. So at least I know where the median is. Finding the median itself, we actually can do that on technology pretty easy, and that's coming up in an upcoming lesson. I think it's the next lesson, actually. And then they mentioned that the IQ scores vary from 80 to 150. Now notice they weren't doing any comparisons here. They were just describing the data from a single data set. So all they had here was context for the pieces that we needed to talk about. All right, lesson targets summary. That means we're at the end. There was a lot of information. In hindsight, where I said the lesson was probably going to split to day 2, that probably wasn't accurate. We'll probably split it a little bit before that, like maybe at stem and leaf plots. So if you were watching this trying to get day 2, you might want to go back and make sure you hit stem and leaf plot. All right, good luck everybody. Happy graphing.